Hi there, guys. So we're going into 8D and 8E now, and they're all about your basic operations with complex numbers and developing the system of complex numbers. And since I've done this before in the HLAA course, I will give you two exercises from there. Bear in mind that the AA course expects you to do more written calculations. And in fact, in the examples for 8D and 8E, a lot of those you can actually use your calculator for. So to get the understanding, have a look at the videos which follow here, and then I'll also provide you with the worked examples in the next video for 8D and 8E here. Okay, so coming up next is some basics on complex numbers now. Hi there, guys. Well, welcome back. So we're finally cracking into the complex numbers section of this chapter. So we're now going on to 3F. And there's quite a lot of little definitions for 3F, none of which are particularly complicated, but it's just building up the idea of complex numbers. I think this is kind of an exciting moment, to be honest, because it's not often that you develop a new system of numbers. So it's pretty exciting. I mean, you know, that when whoever first conceived of these is and said, well, let's just roll with these solutions which are making no sense, and let's develop a whole area of interesting algebra with this. Yeah, whoever did that is great. I mean, I guess it's the combination of many mathematicians over years. In fact, okay, hang on, sorry about that. So in fact, there's a little note actually on here. Did you know? Okay, and just to witter on a little bit about the mathematicians, everything, and the history of maths. It says the first person to propose working with the square root of a negative number was actually Heron of Alexandria back in, what's that, BC 10 to 60? Or is that circa 10 to 60? Okay, but basically around the turn of the first millennium. Okay, so it's 0, 0, 0, you know, when we're measuring time in Christian time, basically. Okay, so when discussing the volume of an impossible frustum of a pyramid, so that's like a chopped off top of a pyramid. But that's interesting, but of course they didn't have all of the algebra back in the day there, but we're talking about this still turning up in the mathematics in the era before the kind of dark ages, if you like. And then, of course, mathematics really took off in the Renaissance, and that's what they talk about afterwards. But in Italy, things are then kicking off again, developing on from a lot of the work which has been found and studied from the Greeks, basically. And yeah, and then that's where it sort of really takes off again. Okay, I'm missing out a lot of maths history there. We're talking about, you know, history of maths being developed in India and the Middle East as well. But you know, a lot of the modern way of writing mathematics and a lot of the more sophisticated modern methods came about during the Renaissance. Okay, anyway, just a little bit here. Alexandria, Alexandria. If you're interested, it's in Egypt. So this Heron of Alexandria came from Egypt, it would seem. And yeah, there we go. Just checking it out on the maps. And the fort looks pretty nice there. Sea looks pretty nice as well. Quite like to go there myself. Okay, and then they talk about later on in Italy, mathematical tournaments became very popular. Solving difficult cubic equations became a way in which they found the winner. So cubic equations actually, just like we have a quadratic formula, there is actually a cubic formula as well, but it's just really nasty. Okay, we wouldn't be teaching that in a course. It's just there are other ways of solving these things. Okay, and those mathematicians discovered the formula for solutions of cubic equations. There we go. That's what they're talking about, and introduced complex numbers. So we have Tartaglia. I don't know if I pronounced that one right, but between 1499 and 1557, and then we're talking about Cardano. And Cardano introduced complex numbers in the form of a plus the square root of b. But in fact, it's not all the way until Euler until we get I being equal to the square root of -1. And there's a bit in between where Descartes is talking about the imaginary part of a number. So which gives an interpretation to the square root of -1. Oh, and John Wallis, I didn't know who John Wallis was. John Wallis is an English clergyman there. Looks like a pretty dour chap, to be honest. Okay, so there we go, a little bit of history on that one. Now, I guess what's also interesting is just building up the mathematics. So we start with our natural numbers. And remember, IB is including 0 in their natural numbers. Some definitions don't. So that's obviously, 1, 2, 3, 4, 5, 6, 7, and also 0. And then you go into your integers, and your integers are including all your negative numbers as well. And then the set which comes after that, which includes all of those things, is then your rational numbers. So this is standing for quotient, but that's rational numbers there. So rational numbers can be written as a over b, where a and b are both integers, and rational numbers come as well from saying a ratio of two things. So a ratio can also be written in the form of a fraction. Okay, and then from there we go on to real numbers, and I know I've talked about this before, but in terms of real numbers, we have both algebraic real numbers, which are the solutions to polynomials, and we have transcendental real numbers as well, which are things like pi and e, which I'm not going to go into now, but and also the algebraic solutions, like for example square root of 2. So that's pretty much everything on our real axis, like our axis for x or our axis for y. That's what we've been interested into up to now. And then we get our imaginary numbers, or rather our complex numbers as we call them now. And the C represents complex numbers. And so that's going to be based on I, but I being your square root of -1. But of course, complex numbers can have real parts as well. So you could have A plus B I. Now, complex numbers include all of the other stuff, because if B is equal to 0, then you're back to having a real number. But this is how we're developing our set of numbers. Now, don't ask me what's outside of the complex numbers. I'm sure there are ways of expanding our sets here, and I'm not proficient in saying how that works. Okay, so that's what we've got, and yeah, so there we go. There's a string here of saying, zoom into this thing here. So there's the string of n is contained within z, z is contained within q, and so on. And that's just saying these things are subsets of the larger sets. Okay, and they're also coming up with z is equal to a plus ib. So they're defining z to be a complex number. So that's saying z is this complex number. Let's get rid of all of this. So if we say z is equal to a plus ib, or bi, let's see which way they write it around here. They're saying ib, yeah. So z is not representing an integer. It's just instead of normally using x and y for our real numbers, we're now saying, okay, let's go to the next setup, and let's say z is defined as our complex number here. Okay, so I'm just flicking through some of the ideas from the book. Oh, and they're saying state the real and the imaginary part of these things. So let's deal this. So real and imaginary part, and let's just take, for example, part D. This will be sufficient. So if I say we've got this real part of z, and we're defining this to equal to our z here, lowercase z, the real part of this, let's say real of square root 11 over 4 plus pi over 4i. So the real part there is not this part here. Okay, it's not the coefficient of I, and of course, if you've forgotten, I is equal to square root of -1, this thing which can't be done. Okay, so the real part of this is just this part here. This part is imaginary, this part is real. So the answer to this is √11/4. Real part of Z is just this front part. Now the imaginary part of Z here is now just the second part. So it's I/4. We don't have to write in the I, it's just saying how much of the imaginary part do we have? How much of I do we have? I is imaginary, that's one lot of I, but how much of it do we have? So we don't need to include the I there. Okay, so we can obviously write these on diagrams as well, and they're talking about both the algebraic approach and the geometric approach as well. And this little diagram which they draw is the argand diagram. And they talk again a little bit of historical stuff. They say that this was also called the Gaussian plane. You can see that Gauss had his fingers in the pot here as well. So he's interested in this one too. And we have Jean-Robert Argand, I guess you pronounce it in the French way, first proposing the idea of putting these things on a coordinate plane. Now, this is a Cartesian way of representing our complex number. We'll talk about other ways of doing that later on. So, for example, we could put it in a polar form, but we'll talk about that later on. So the Cartesian form is actually like, let's get rid of everything here. Okay, so when we say Z equals A plus BI, that's the Cartesian form. So, for example, if we had Z equals 2 plus 3i, when it comes to putting it on this argand diagram, we can say that that's essentially 2 across, so we can space this thing out. So it's going to be 2 across, and it's going to be 3 up. I might have to change the scale a little bit on this one. And it's going to be 3 up. So we're going to put this coordinate point here, and that's the geometrical representation of this complex number. Now we need to just label this as imaginary and real. Now I have seen that sometimes they put on I here and 2i and so on, but simply because we're talking about taking the imaginary part of Z being equal to 3, you can just leave the scale in terms of numbers and you don't need to put those i's on. It's understood that that's going to be 3i. But I have seen that some people put the i's on those axes. I think it really doesn't matter too much, to be honest. Okay, right. Now, I think later on they start talking about the modulus of Z, and I might as well just deal with that now. The modulus of Z is basically the length of this complex number on the argand diagram. In other words, that's using Pythagoras to work out the length. So the modulus of Z is talking about taking the real part of Z and squaring it, and the imaginary part of Z and squaring it, and adding it together and taking the square root. So that's just a definition for the modulus of a complex number. It's basically just saying how long is this complex number? What's the distance from 0, 0 on the argand diagram to this complex number? So that's the meaning for the modulus. It's basically saying what's the size of this thing. Okay, when we're saying the modulus, we're often saying what's the magnitude of something, and the magnitude of this complex number is going to be this distance here. Okay, so that's just picking that one up as well. Oh, that actually does turn up next. Surprises me there. So there we go. And there we go. We're talking again about, just to find that one, that's the modulus. And you can see they've just added another little bit there. They've actually added in, just take this, they've added in this bit here. They said, oh, that's the modulus of x plus yi. Now I did it in terms of a and b, and that's fine. They've done it in terms of x and IY. So there you go. A YI or IY. Put the I first. Okay. It's interesting to note that the modulus of this is always actually a real number, because there's always a real distance to how far we are on the argand diagram. So we're only going to get out real answers to that. We're only actually putting in real numbers there as well. We're not putting in any i's. Okay, so then we've got example 12. Let's take this. Okay, so find the modulus of the following complex numbers. And again, let's just take this one here. Let's just do one of these. So again, we're doing the real part of z, of course, z, and squared plus the imaginary part of z squared and square root this thing. Now, we need to split this one up a bit, don't we? So we need to say that this is a 21 over minus 21 over 29, and then plus 20 over 29i. We can see that the real part of this is going to be minus 21 over 29 squared, and the imaginary part is going to be 20 over 29 squared, and then we can square root that thing, and that's going to give us our answer. Now check your answer with your GDC. Well, you can set up complex numbers on your GDC, and then you can take the modulus of those things as well, and it's all pretty straightforward. I'm not actually going to deal with that at the moment, but have a play around on your normal scratch pad. You can make complex numbers, and you can find the modulus of them as well, and those functions are defined on your calculator, so you won't have to actually do this. Okay, now there we go. So there we go. I mean, you can see, let's just take that here actually. So you can see what they're doing on the calculator there. They're actually saying, look, come up with your modulus brackets, and you can put in 20, what is it saying, 20 times I? 20, oh yeah, no, 20i, but they've put a times in there. Okay, that times is a dot, minus 21 over 29. Sorry, yeah, I was thinking that was the first and second. No, that's yeah, that's right, that is a times. Okay, so that's what you're going to get off your calculator, and you can just use the modulus brackets and it will do it all for you. So you don't need to use Pythagoras if you're typing these into your calculator. What's kind of interesting with that, just to say, if you were trying to solve Pythagoras, you know, if you were trying to say, I don't know, what's the distance between 2 points, and let's say we've got, I don't know, 3 squared plus 9 squared is equal to x squared. If we actually want to find that out, we could set up a complex number by saying we've got 3 plus 9i, or i9 if you want. I would put the I afterwards there. So 3 plus 9i, if we set that up as z, then we could just do the modulus of z. We define that to be the case. Or we can just put in 3 plus 9i and do the modulus, and it will actually solve this Pythagoras for us. Okay, so there are links between complex numbers and geometry. And in fact, later on, I think some programming uses complex numbers in order to make movements on coordinate grids. And we might talk about that later on. So there are these links between geometry and complex numbers, and sometimes using complex numbers is really easy. For example, in doing rotations, it's really easy to do combinations of complex numbers to make movements, and that can be used in programming, I believe. Okay, so operations with complex numbers, we're nearly there. They're talking about you actually filling out a table here in an investigation, but I mean, this is all relatively straightforward stuff. So it's basically saying you can add together complex numbers and times them. So it's leading up to this statement here. It's talking about the algebra behind complex numbers. If you have two complex numbers, here we go, in this box, it's pretty important, but it's also pretty obvious. If you have two complex numbers, then you can add together their real parts, and then you can add together their imaginary parts, and you can factorize out the I there. And it's pretty obvious stuff, really. And then if you're going to times by a scalar, so z times by lambda in this case they're using. So this thing here is lambda. Often mu is used as well. Okay, so they're just more Greek letters that you should be aware of, which are often used in mathematics. So if we're timesing by lambda, we can see that that's the same as timesing real part and timesing the imaginary part. So you can essentially bring that scalar on the inside of the complex number. Now, that leads to a pretty easy set of questions, example 13, before we then do the exercise. So it's starting off nice and easy, obviously, because we're building up from the very basics in terms of the algebra here. Now, so for A, when we say Z1 take away Z2, that's 4 minus 3i, take away minus 2 plus 5i. When we do that, that's obviously giving us 4 plus 2, minus 3i there, and minus 5i. We combine that to give us 6 minus 8i. So that one's done. Okay, and then for this one here, it's very similar. We're timesing the first one by a third of this thing here, and then plus 2/5 of Z2, which is minus 2 plus 5i. And you can just multiply these out. 4/3 minus I, and then plus, not plus, minus 4/5, and then plus 2i, and then you can combine those things as well. So put those fractions together, and then put the i's together to give you 1i. Okay, so you can check those ones on your calculator as well. There are the answers. I suggest that you have a go at some of this in 3F. All relatively straightforward for the time being. It will soon get quite a lot more complicated, so enjoy it while it lasts. Okay, guys, well, thanks for listening in, and well done for your effort so far, and I'll see you for 3G. Hi there, guys. Well done for doing 13F. We're about to do 13G here, and this is where complex numbers become much more sophisticated algebraically. So this is a really important exercise which we're building up to here. We talk about multiplying out multiplying two complex numbers, dividing two complex numbers, the complex conjugate. So there's quite a lot of algebraic stuff which is going on here. Just before we get to that, though, just a note on the calculators. Now, we use the TI Inspire CX model at my school, and obviously, if you don't have this, you'll have to figure out how your calculator works. But just a little note on this one, it may be similar with your calculator. If we do, for example, 3 plus I using the keyboard at the bottom, then it will not understand that, because the imaginary part of the complex number, in other words, I, needs to be found through the particular key. So it's not defined by I as the letter, it's defined by defined through, in fact, the pi key over to the bottom left. So if you see the pi key at the bottom left, little arrow on this one, and it leads to a whole load of little commands, and one of them allows you to put in the square root of -1, in other words, I. Okay, that's one thing to note there. And second thing to note is your calculator still won't be able to do that. So for example, if you type in the square root of -1, unless you've changed the settings to accept complex numbers, it will say, we don't understand the square root of -1. And so in order to accept complex numbers, and in order to accept that the square root of -1 is I, because your screen on your calculator will give you I out for that answer, you need to go to menu. You need to go to the main screen and go to settings. So number 5, settings on the main screen. and then you change where it's talking about the real form. It probably says real form already for you. There's an option for you to choose either rectangular or polar. So go into rectangular for the time being. So that's going to allow this Cartesian form for answers for complex numbers. Cartesian form being things like a plus bi. That's what I was talking about a moment ago when I was talking about 3 plus I. Okay, so there's another way of doing that. If you want to go to Scratchpad and you're just working on there and it's not accepting complex numbers, you can go to Document and then to Settings that way. So you just need to change your settings from real to rectangular. Okay, right. So let's have a look at the next little bit. So there's a good little investigation here, this investigation 7. And this one is worth doing. It says use your calculator and your algebra skills in order to fill out the following. So it's building you up with this Z1 times Z2. It's getting you to question, how is this done? And in fact, then we get this little box saying, well, actually, here we go. Here's timesing together two complex numbers. So let's just take this. Okay. So this one is saying, well, how do we do this? Well, here's Z1, here's Z2. We're defining Z1 in terms of A plus BI in this Cartesian form. Here's Z2, just the times in between those two brackets. They're making that explicit. And they're saying, well, how do you end up getting your final answer? Well, you get it in this fashion here. Now, I'm actually going to do this through an example. So let's do an example here. So let's say, for example, we've got 3 plus, I don't know, 2i, and then we have, let's keep it simple, let's say 2 plus 5i. Okay, so when we multiply that out, we've still got the 4 things that are going to come out from this. In other words, your FOIL, if you like, firsts, outers, inners, lasts. So we're still going to get the 2 terms from the first bracket timesing by the 2 terms from the last bracket, giving us 4 terms. Now, that's 6, and 3 times 5i is going to give us 15i, and then 2i plus 2 is going to give us 4i, and then 2i times by 5i gives us 10i squared, because we'll get I times I in there. Now, of course, I is the square root of -1, so when we square that, it takes us back to -1. So this thing on the end, this can just be seen as changing the sign here. Okay, and in the definition, you'll see that in terms of bi times di, and that gives us this minus bd here to add on to the non-complex part, to the real part of this number. So this is basically giving us 6 take away 10 plus 15i plus 4i. And so you can see this is just exactly what's happened here. It's just written in what's looking like a complicated form, but in fact it really isn't. Okay, so you can obviously simplify that one at the end. So we're getting -4 and then plus 19i in this case, and that's the multiplication of 2 complex numbers. Okay, that's pretty straightforward. Okay, and then they give you a whole lot of practice with this, and it's a good idea now just to stop this one up and give this a go and check this with technology, but I'm going to go through a few of these. Okay, so let's have a look at this. We've got the first one, the second one, timesing together, and then taking away the third here. So this should be pretty straightforward. Times by 4 plus I, and then take away the third one, which is take away -2 plus 3i. So multiplying this first one out, we're getting 4 and -12. Put the other way around, let's do this times this. I, and then plus I, and then -12i. And then we've got 3i times I gives us -3, and the minus there is going to bring that back to +3. Okay, because of course, -3 times +1 gives us -3, but then we need to change the sign. The because there's an I times an I. Okay, and then at the end we've got minus, and obviously minus minus 2 is plus 2, and then we've got minus 3i there. And then it's just a simple case putting everything together. So we've got 4 plus 3 plus 2, so that's giving us 9, and then we've got minus 14, lots of I there, I think. Okay, let's just check this. Yeah, minus 14i. Okay, you can obviously check with your calculator, and it's a good idea at this point to have a go at this with your calculator as well. Okay, next one, we've got the multiplication of 3 brackets essentially here. So, well, we did the multiplication of Z1, Z2. Z1, Z2 gave us out 7 take away 11i. Okay, so 7 take away 11i is the multiplication of these two. We essentially did that last time around. So just beating a little bit here, using the previous answer. And then obviously we can multiply these ones out as well. So we've got minus 14 and minus 21. That's right. Yes, minus plus 21i, sorry. And then we've got plus 22i, and times in the last two things out, we've got 33 minus 33i squared, which brings us back to plus 33. So we can see here we're getting 19 plus 43i. Let's just check we've got that one right. Hurrah, we got that one right. Okay, and for the last one then, okay, so yeah, for the last one, I mean, so these are fairly straightforward. So we've got Z1 squared, square of this, do this, and then we've got 2 lots of, and then we've got the other 2 ones to minus 2 times together. So we've got 4 plus I, we've got the minus 2 plus 3i. Okay, and again, it's just a matter of lines of working out and being accurate in this case. So multiplying this one out here, getting 1 minus 3i, 1 minus 3i. We multiply that out, we're getting 1. We're getting 2 lots of the middle term, so we're getting minus 6i. And then we're getting minus 3 times minus 3 is plus 9, but then, of course, the I times the I brings it back to minus again. So we're getting that for this one here. Okay, so that's the expansion of this. So I'm just going to put a line through that one there. And then we've got minus 8 plus 12i minus 2i and minus 3 coming out. The timesing those two together, we need to double all of that, of course, and put a plus on there. So, you know, it's just lines of working out. If you're skipping through this, perhaps you've done it yourself. And we've got, so I'll simplify this first, actually. Let's just simplify this. We've got minus 8 minus 6i. And let's simplify what's inside the brackets here. Okay, so I'm doing my full working out this time around. And we've got plus 10i. And then again, we've got 8 minus 6i, and then minus 22, and plus 20i. So finally, we're getting plus 14i and minus 30 here. So let's just check that one, minus 30 and plus 14i. Okay, and they're saying check this on your calculator as well. That's interesting. They're actually letting these expressions equal to Z1, Z2, and so on, and then they're using them in the calculation so that they don't have to write them out each time. Okay, I was just needing to recap how to do that as well. You can use the define function in your calculator to define Z1 is equal to your complex number, whatever you choose it to be. You know, if it's 4 plus 3i, then you can say define and write in Z1. And so you can just type in the Z from the key at the bottom and then 1, and then equals 2. And to use the equals there, we're not pressing enter for equals. We're using the key on the left-hand side underneath control to say equals, and then we're setting it equal to our complex number. And then when you press enter, then it will say done. Then when you use that again, you can say Z1 times, if you've defined another complex number as Z2, you can just do times Z2 and that will work. Interestingly, you can do more than just defining complex numbers there. You can define functions as well. So in this case, you could come up with what is f of 1 if you've defined this function, which you can see here, and then it will give you out the answer to that. Okay, so that's an interesting little function. And you can find the define key by going through menu and then actions and then define. So it's pretty much the first of all of your options. Okay, right, so let's go back to the book and got example 15 here. Okay, so example 15 says find Z belonging to the complex domain, complex numbers that satisfies this equation here. Use technology to check your answer. Okay, well, there's two ways of doing this question. And let's just take this further from what we've got here and see where we're going to get stuck in one of the ways. So let's just say, let's multiply it out, which is, I guess, a fairly obvious thing to start off by doing. So we've got 2 times Z minus Z times I equals Z plus 3 plus 2I. And then we can bring all our z's together. So we can take this z over to the other side and we'll get z here. So take it off 2z there. And we've got minus zi equals 3 plus 2I. And then we've got, we can factorize out the z. So we've got 1 minus I lots of z here equals 3 plus 2I. And now we can do our division. You can say 1 divided by I. Now that is right. It's just that we don't like to have complex numbers on the denominator or in the denominator if we can help it. It's a bit like, for example, when I say 1 over the square root of 2, we don't normally write 1 over the square root of 2 like that. We write it like this, square root of 2 over 2. We rationalize the denominator. And it's the same with complex numbers. We need to sort of all agree on how we want to standardize our answers. So this one, we would times the top and the bottom by the square root of 2 to give us this answer. And, just a recap on this, if we had 1 plus the square root of 2 here, then we'd need to times by 1 minus the square root of 2, the conjugate of this number involving surds here. And 1 on top, 1 minus the square root on top. And if you do that, you'll notice, back to a little work with surds, you'll notice that the two middle terms here disappear. So we've got 1 and these two times together. So we'd end up getting minus 2. And we get 1 over square root of 2 on top. And so, of course, this can become minus 1. And we'd end up getting square root of 2 minus 1 on top, and we divide by minus 1. Okay, so that's how we deal with the issue with surds. Now, we deal with this in exactly the same way. So where I was saying previously, let's wait until we get stuck, here we're stuck because we don't have z as in z equals to a plus bi. Okay, so here we're stuck. So we're going to use that same trick. And this is actually looking forward to the next set of questions, in fact, but we might as well do it here. And then we'll do this question in a different way as well. So this one is saying we can do 3 plus 2i. And this one now we're timesing by the complex conjugate. So 1 minus I here, and then we're timesing that by 1 plus I over 1 plus I. Let's just put those in brackets, make it clear what we're doing. And then when you multiply these two things out on the bottom, you'll notice that the two middle terms disappear again. And so you'll end up getting 1 times 1. So we'll get 1 there. And then we'll get I times I, which is minus 1. And we have minus there as well. So that's, again, plus a 1. And then on the top, we're getting out 3. And I'm just going to do my whole numbers first. So I'm going to do this times this. So minus 2. And then we're getting 3i. And we're getting 2i there as well. Okay, so the answer to this is going to be 1 plus 5i, but both of those are divided by 2. So I'm just going to split it up into that form, a plus bi. So there's our z, our complex number, there's our real part, and there's our imaginary part here as well. Okay, so that's how we can deal with that. It's interesting to note that on the bottom, when we times these two things together, when we times a plus bi times by its complex conjugate, a minus bi, that you're getting out a squared plus b squared there, which is the same as the modulus of this z being our original number. So we're doing z times by its conjugate, as well say now we call it z star. Okay, and the result which you're getting is actually the modulus of z squared. In other words, like Pythagoras, but without square rooting it. So modulus of z would be this square rooted, and we square it, and we get back to this thing here. Okay, that's actually a little result. Really going ahead here, not really finishing example 15, but there we go. This is equal to this. Right, okay, so I've actually done the next bit of teaching. So there's the final set of answers. However, there is another way of doing this where you don't need to do the division of complex numbers, which we've just dealt with. So let's take all that back and let's set it up by saying, less obviously, I think, that z is going to be a plus bi. Now, when we're multiplying this out, I mean, you might have thought this a bit strange because when we do z times I, z includes some imaginary part. So when we're saying zi, well, you're like, well, yeah, sure, some of that is imaginary, but some of that is real as well, because z includes an imaginary part, and an imaginary part times I is going to lead you back to a real part. So there was that problem of not separating out imaginary parts and real parts, and we can solve that problem by setting up z is equal to a plus bi. If we do that, we've got a plus bi z times by 2 minus I is equal to, and again, a plus bi plus 3 plus 2i. Okay, so if we multiply out the first set of brackets, you can get 2a, and I'm going to deal with the real parts first. So we're getting minus b times I squared brings you back to plus b, and then we're getting 2a, no, sorry, not 2a, minus 2 minus ai, and then we're getting 2bi as well, so plus 2bi. Okay, and on the other side, we're getting a plus 3 as our real part, and we're getting bi and 2i as the collecting together of our imaginary parts. Okay, so now we've got 2ab on the left-hand side. Just give ourselves a bit more space here. We've got 2a plus b for the real part there. Now that's got to be equal to the real part on the other side. So that's got to be equal to a plus 3. And then we can set up another equation with the imaginary parts. Because really we can say that this, that what's on one side of this equation has to be the same as what's on the other side in terms of its real part and its imaginary part. If this is ultimately a complex number, then it's somewhere on the argand diagram, and this is the same at the same place on the argand diagram. So we can split this now into two equations, by comparing the real part of the left-hand side and by comparing the imaginary part of the, and equaling that to the, I should have given myself more space, equaling that to the real part of the right-hand side. That's essentially what we've done there. And of course, we're going to do the same by doing the imaginary part of the left-hand side equaling to the imaginary part of the right-hand side. I'll give myself enough space again. There we go. So imaginary parts here. Let's have a look at this. Well, if we factorize out the I, we've got 2b minus a, lots of I here. And on the right-hand side, we have 2 plus b. So you can see what we've got. We've got two simultaneous equations which we can now solve. Obviously, you've got either your calculator to solve those, or you can spend some time solving them. Now, from my point of view, this question is actually longer by this method, and it's not necessarily obvious to do this at the start. I think most people would just, crack on with the algebra without doing too much thinking. So anyway, this leads to two simultaneous equations. I'm not going to solve them now. You can see they're getting 2a plus b is equal to a plus 3. Just check that I've got that right. Yeah. And we've got minus a plus 2b minus a plus 2b is equal to 2 plus b. And there we go. We're ending up with two simultaneous equations. And the set of solutions there, 1 and 5 over 2. Of course, that leads to the same solution as we had before. Okay, you can check that on your calculator. But there we go. We've already talked about complex conjugates, which is the next bit. Let's look at this. So if you're just skipping through this video and you've missed the bit, we've actually talked about this in the previous question. So conjugates got z is just equal to a, b, I, and the complex conjugate you just call z star is equal to a minus bi, just like with surds. I did check out earlier on what's the definition in maths of conjugate. It says a math conjugate is formed by changing the sign between two terms in a binomial. Okay, so your a plus b becomes a minus b. Okay, so there's a little bit extra on that definition. It says that the real part of z is equal to the real part of the conjugate. In other words, a is equal to a, and the imaginary part of z is equal to minus the imaginary part of the conjugate. That's just an alternative definition, essentially. Okay, right, so there's plenty more questions here, so let's get on. It says example 16. So example 16 is very similar to what we were talking about before. It says, given these two complex numbers where z2 is not equal to 0, so when we're not dividing by 0, and a, b, c, and d are all real numbers, so the coefficients are all real numbers, find the division of these two things. Okay, so now we're working in algebra, and this is a good one to stop and to do yourself, and then just check with me, check out with the answer in a moment. Okay, so we're going to times this one. This is our z1 over z2 times by complex conjugate. Okay, and so on the bottom, we've already done this in the previous exercise. We'll see the two middle terms disappear. So we get c squared minus d times plus d, but then I times I gives us a negative 1. So we're going back to plus d squared. And again, you can see that this is equal to our modulus of z all squared. And on the top here, you're getting AC minus BD. Okay, and this is essentially using the definition from before, and then plus BC and A times by minus d in this case, and a times minus d is minus ad. Now I see I've made a mistake there. I don't know if you can see it as well. Because previously we were using plus here, in fact that changes to a plus here as well. So that was because b times by minus d gave us minus bd, but of course I times I gives us minus 1. So there we go, there's the real part, and this is the imaginary part on top. And I think that is done. Let's just see what they write in the book. Well, yeah, they've just split it up into a real part, and an imaginary part separately. So they've just said, at this point here is our real part, and here is our imaginary part. Okay, so they've written it out fully in order to define what the real and imaginary part is separately. C squared, d squared, and then plus bc minus 8d over c squared plus d squared I. Okay, so there's your final answer. Okay, next question. And they go through the point which I explained earlier as well, that timesing z by z star conjugate gives you z, the modulus of z squared. In other words, a squared plus b squared. Oh, and there's another thing here. There's the definition here. They're saying, well, when you're doing your division rather, z1 divided by z2, it's the same as timesing z1 by the conjugate of the thing on the bottom, and then having the modulus of z2 squared on the bottom there as well. Okay, now from my point of view, once you've got lots of practice, you won't need to spend time remembering this. You'll just know that one. That will become really quick. Okay, 2 more questions, I believe. So again, lots of algebraic work here. You might want to stop this up and have a go at this yourself. And so it's saying we've got z1 divided by z2, and then take away 3 lots of z3. And I mean, these are very, very similar, these questions. So I think maybe I'll just go through one of them. So I'll go through A, and then you can have a go at the other ones. They're just practice, essentially. So first one here, we've got 2 plus I divided by 2 minus 5I, and then take away 3 lots of Z3. So we'll take away 3 lots of 2I minus 1. Just flipping that around. So this is part A. Now, the left-hand side is going to give us 2 plus I times by the conjugate of what's on the bottom there, and then 2 minus 5I times by that conjugate. I would still write that all out, and then minus 6I, and then plus 3. Okay, so when we're timesing the thing out on the left-hand side here, we're getting 4 minus 5 plus 2I plus 10I, all divided by 2 squared. So let's just put in 4 there, and plus 5 squared, so plus 25. Now take away 6I plus 3, and we can see that this thing here is all going to be over 29. So we've got minus 1 over 29, and then plus 12 over 29I, and then plus 3, and then minus 6I. So you can obviously then combine this and this, and you can combine this and this for the amount of I which you have there. Now, that means that you're going to need to change these into fractions out of 29, so times the top and bottom of both by 29, which is a fair bit of work if you're doing that without your calculator. Okay, so next question, and you can see what they've done there. And I'm not going to take the other ones forward, but you can see what they've done for part B. The answer should be 12 plus I over 29, or 12 over 29 plus 1 over 29I. And you can see what they've done for C as well. It's pretty straightforward stuff. Okay, and example 18, I believe, is our last one before 3G. So let's have a little look at this one. So example 18 says, find Z belonging to C that satisfies this equation here. Now, this is kind of interesting because how do you set this one up? Do you go back to saying Z is A plus BI and work with that, which is going to create a lot of working out here? Or do you try and get as far as you possibly can just with using Z and then see where you get stuck? My suggestion would be try and take this as far as you possibly can, but be aware of the fact that Z is A plus BI. So let's try and do that. So we've got Z plus 2 times by 2 plus I equals 2 minus, not 2, Z minus 3I, then 1 minus I here. That's just our cross multiplication. And then when we multiply this out, we're going to get 2Z. So what have we got? We've got 2Z, and then we've got plus ZI plus 4 plus 2I. And then on the other side, we've got Z minus ZI minus 3I, and the last term is going to be plus 3, but then the I times the I gives us a minus, so back to minus 3 there. Okay, now let's bring all of our Z's together. So all of our Z's together, because we're trying to find Z is equal to something. So this time I'm not bringing all of my imaginary parts together nor my real parts together, because frankly, this includes imaginary and real parts. So let's just bring all the Z's together. So I'll bring the Z's to the left-hand side. So we've got Z of 2Z gives us Z, and plussing Zi onto Zi is going to give us plus 2Zi. And then on the right-hand side, we're going to take off the 4, so it gives us minus 7, and take off the 2i. Remember, we've already dealt with those ones, so take off the 2i from this, and we're going to get minus 5i here. Now, we're trying to get x as the subject, so we're going to put factorize out the z there, so we've got 1 plus 2i equals minus 5i minus 7. We can do our division, of course. Minus 5i minus 7 over 1 plus 2i is equal to z. Now, again, it's not good enough to leave it like that. And that is partially done, but you'll probably lose a couple of marks by not giving it in the correct form. And probably an exam question will say, can you give your answer in this form where a and b are rational numbers or are real numbers? Okay. So we need to take this a little bit further, and in order to do that, we're going to times, take it over to this side, we're going to times by the complex conjugate. We've got minus 5i minus 7, and then times that by 1 minus 2i. And then, of course, on the bottom, we've got 1 plus 2i. I would just make it really explicit as to what we're doing. And on the top, we're getting... So we're getting, let's do minus 7 first times both of those things. So we've got minus 7. Actually, let's then do this times this is do real parts. So we're getting minus 5 times minus 2 is plus 10. So go back to minus 10. And then we're getting minus 5i, and we're getting plus 14i there. On the bottom, we're getting 1 squared plus 2 squared, so plus 4 there as well. Okay, so now we can hopefully simplify this and get the final right answer. So we're getting minus 17 and plus 9i, and then divided by 5, and then we can split that up into 2 parts. Minus 17 over 5 plus 9 over 5i, and then there we go. That's our final bit and we are done. So let's check that answer. There we go. I feel very relieved when I've got that one right, because it's these lines of working out cause a lot of easy mistakes, and the easy mistakes are made when are made with the negatives. And there's the fact that we're doing I times I just compounds the chance of getting negative mistakes through our lines of working out. So do use lots of lines of working out. Okay, right, well, there's that, and they've checked it on the calculator, which you can do as well. And we got to 3G, and really you need a lot of practice with this. You want to become really proficient with all of these skills. So this one, I'm sure, goes on. There we go. Goes on to part 8, and there's some nice little proofs towards the end here. So they're saying prove the following properties of these complex numbers. And when you're making those proofs, you might want to set up Z is equal to A plus BI, and you might have to set up Z2 as C plus DI, and then work with those two things. So take the left-hand side, take the right-hand side, and end up with similar expressions. Okay, right, well, that's a lot of stuff in one exercise. Next time around, we're dealing with powers and roots of complex numbers, but good luck with the exercise. Thanks, and see you next time around.